Now we come to the second part of Chapter 10, Unit 2. Unit 2 deals with the ideal gas equation, which we sort of started towards the end of Unit 1. And so now I'm going to share my screen and start the Unit 2. Now, what does the Unit 2 consist of? So going right up, we're going to start. First thing is we're going to study the objectives for Unit 2. Basically, it is the beginning of ideal gas equation and its applications. We have to understand the origin of the ideal gas law and how to use the equation. Then we will relate the gas density to molar mass, pressure, and temperature. Calculate the molar mass of a compound from the pressure of a known quantity of gas in a given volume at a known temperature. And beyond that, we will just go along and see how these expressions are used in stoichiometry, and some self-study questions will be included. So here, when we combine the Avogadro's hypothesis with the general combined gas equation, we get the relationship that PV over NT is equal to a constant. And then in order to remove the word constant, we replace it with the letter R, which is called as the gas constant, thereby giving you the ideal gas equation as PV is equal to nRT. The value of R, which is called as the gas constant, is obtained by using the standard STP conditions. What are the STP conditions? The STP conditions are when the temperature is at 0 degrees C and the pressure is 1 atmosphere, then it is known that all gases occupy a volume of 22.414 liters, as we saw by the slide on which the various different types of gases were introduced and their volume calculated under STP conditions. So with that, knowing that, we can then use how to calculate the ideal gas equation and what its values are as we go along. So PV is equal to nRT. R is the proportionality constant. Ideal gas is a hypothetical gas whose pressure, volume, and temperature properties are accurately described by the ideal gas equation. Now, we see that all gases do not behave like ideal gas, and therefore we have to deal with the real gas. And the real gases will approach ideal gas behavior when the pressure is very low and the temperature is high. Now, how to calculate the gas constant value? The value for R is obtained by using the ideal gas equation PV is equal to nRT for 1 mole of a gas under STP conditions of 1 atmosphere, volume being 22.414 liters, and the temperature is 273.15 K with their units. When we solve that, we can get the value of 0.082056506 liter atmosphere mole Kelvin. The numerical value of gas constant under different units as provided here. So if you have like the units are in liter atmosphere mole Kelvin, then the value is 0.08206. If it is milliliter atmosphere mole Kelvin, then it is 82.06. Now, if it is a cals per mole Kelvin, then it is 1.987. And if it is joules per mole Kelvin, that is 8.314. Because these values of R are important as we go along, because we have to use the gas constant many times for different calculations. Now, and here, so how do we calculate So this is how to use the standard temperature and pressure and then calculate the volume occupied by different gases. And again, we have the equation we are going to use is the ideal gas equation, and then we're going to find out the volume. So in order to provide a reference point for the comparison of gases, standard temperature and pressure are set at 1 atmosphere, 760 torr or mmHg, and 0 degrees Celsius to 73.15 K. Calculate the volume. That's the problem. Calculate the volume occupied by 43.7 grams of hydrogen at STP. So now we have the grams of hydrogen, 43.7. We've got to convert it to moles of hydrogen. So we divide it by 2.02, taking the atomic mass of hydrogen as 1.01 grams. Then multiply it by R, which is equal to 0.08206 liter atmosphere mole Kelvin, and divide it by the pressure, 1 atmosphere. Don't forget to multiply this number by 273.15. So because the volume is equal to nRT, so remember to multiply the numerator by 273.15 to get the answer of 485 liters. The make note for the ideal gas equation, always convert the temperature to Kelvin, convert from grams to moles if necessary. Be sure to convert the units of R, liter, atmosphere, mole, and Kelvin, and make sure that you convert the temperature. So a gas, this is another problem. A gas in a 250 milliliter flask has a pressure of 1.3 atmosphere at a temperature of 31 degrees C. How many moles of the gas is present? So in order to solve this, what we have to do is convert the volume to milliliters, and to do from milliliters to liters. So what we do is divide it by 1,000, so that you get the flask, the volume of the flask will be 0.250 liter flask. Convert the temperature of 31 degrees Celsius to Kelvin by adding 273.15, so that you get 304.15 Kelvin. The gas constant is R, so 0.0826 liter atmosphere mole Kelvin, and then you can calculate the moles of the gas, because the moles of the gas, N is equal to PV divided by RT. Substitute the values and you can solve the problem. Now, using the ideal gas equation, how to calculate the density of a gas? We know that the number of moles is mass divided by the molar mass in grams per mole. Substituting N in the molar mass in the ideal gas equation, we get 4N. We get PV is equal to M divided by capital M times RT. On rearranging, M over B is equal to PM divided by RT, and M over B, by definition, is density of a gas, and its units are grams per liter. We can see how what effect the material or the substance of a gas has when you try to fill it up with a balloon. The density of air is much larger than the density of helium, and so we see that helium stands up while the rest of the gases are down. Balloons are down because it is heavy. So what is the density of oxygen under STP conditions? Now, under STP conditions, we see that the density of the gas is equal to Pm over RT. The molar mass of oxygen is 32 grams per mole. And so M over V is, we have the pressure is 1 atmosphere, the molar mass is 32 grams, the gas constant is 0.08206 liter atmosphere mole Kelvin, and the temperature at STP conditions, the temperature is 273.15. When you substitute it, you get 1.428 grams per liter. Now, we can use the density. Once we calculate the density, it is also possible to identify the molar mass of the gas or molecular weight of the gas. So once we get the molar mass of the gas, then we can identify which type of gas it is. So here, in this problem, you're given the pressure and the atmosphere. Pressure and in atmospheres and the temperature in Kelvin. And you're asked to find out what is the density of the gas. So we go back to the previous, that PM. So I'm going to solve it over here. How do we solve it? Where it's very simple. Density is equal to PM divided by RT. So we know that all the factors are given. We have the density is given, the pressure. So we can substitute for now. Let's go and substitute it. Substitute for the terms 3.57 grams per liter. Grams per liter is equals, the pressure is 1 times the molar mass divided by 0.08206 times 300 K. 300 K. Now all we have to do is solve this equation. How do we do that? The solution is very easy. 3.57 times 0.08206 times 300. And if instead of 100, we make it to 300, and then we solve it, and we'll get the molar mass. 300. We can calculate this number and see what the answer will be. I'm going to leave it for you to do it. And then, once you get the molar mass, look at the periodic table, remembering that the gases, many of the gases are diatomic, and therefore you can find out what is the gas, what gas it would be. Now, and so density and molar mass. Density is directly proportional to the molar mass. Density is equal to P molar mass times RT, and therefore this can be derived from PV is equal to nRT. Now here are some problems. I don't know if the video works. No, it doesn't work. So we're going to remove it. If it doesn't work, if the ideal gas law problem sheet doesn't work, there is another under watch. The same sheet is available. And so you can watch the video and see how to solve the different types of problems that are there. So in order to calculate the molar mass from pressure, volume, and temperature data, determine the molecular formula of a compound. Then we can also use this to find the empirical formula of the gas, mass of the gas, pressure of the gas, volume of the gas, and the temperature of the gas. So these are some of the applications of the ideal gas equation that can be used. So in order to calculate the molar mass per PV and T, calculate the density of the gas, determine the molar mass of the gas, and determine the molecular formula of the gas from its molar mass and its empirical formula. So this is basically based on stoichiometry. So you have gases and stoichiometry. Remember that whenever you do stoichiometric problems, you have to always use a balanced equation. So how many liters of carbon dioxide are produced from 0.5 liters of oxygen gas? Substitute and solve. Again, this gas stoichiometry problem, you can check it out under the video section, watch section, and you'll be able to see it. So now this is an airbag problem. If you get into a crash, the airbag opens up. And so again, this is an application, a real life application for gas law that is there. And it's based on stoichiometry. The safety airbags in automobiles are inflated by nitrogen gas generated by the rapid decomposition of sodium azide NaN3. So NaN3 breaks up into sodium metal and N2 gas. How many grams of sodium azide are needed to generate 60.0 liters of nitrogen at 1 atmosphere and 26 degrees Celsius? So first you convert calculate the moles of nitrogen that is produced from the reaction. So for every 2 moles of NaN3, 3 moles of nitrogen gas is produced. And so using the volume of nitrogen gas as well as the liters, you know the number of moles that is produced. And at a particular temperature, convert the temperature to Kelvin, and then substitute it in the equation and solve it. Next is the Dalton's law of partial pressure. The total pressure of a mixture of gases equals the sum of the pressures that each gas would exert if it were present alone. So basically what it says is P total is the sum of the partial pressures of the gas inside the container, on the assumption that the gases do not react with one another. So here you have a pressure, and then when you add it up, the total pressure is 183 millimeters of nitrogen in one gas, one bulb, and in the other bulb you have 0.005 moles of oxygen. Nitrogen and oxygen under normal conditions do not mix with each other, and therefore there is no reaction. The total pressure would be the sum of 186 mm pressure plus 93 pressure, which gives you the outer flask, showing that when they mix together, the total pressure is 279 mmHg. The pressure or the mole fraction of nitrogen would be 186 divided by 279. The mole fraction for oxygen would be 93 divided by 279, because we assume that the temperature and the volume is kept constant. So now, as I indicated verbally, by showing you what the total pressure, partial pressures would be. So now we substitute it, because the P total would be the sum of the moles of all the gases, the present. You add them up, multiplied by RT, and divided by V. Therefore, we can see that the total pressure will be N total times RT over V. Each gas gas can be represented as a fraction of the total moles in the mixture, and this is called as the mole fraction. Since each gas adds together to create a total pressure, the molar fraction that represents each of the individual gases is akin to a concentration. So we can do that Ni over N total. And so this is how we solve the mole fraction for the problem. The partial pressure of the first gas divided by the total will be Ni RT over V over N total RT over V. The term RT over V is constant. And since temperature and volume are kept constant, therefore we see that the partial pressure for any gas is the mole fraction times the total pressure. And this is a very useful equation to calculate the number of moles. So if you have Na as the partial pressure and Pa is the partial pressure, so Na is the partial moles, N total is the partial total number of moles is the same. Mole fraction can be substituted either in terms of moles or in terms of pressure. And this is the same derivation that is done above, and I'm sure this won't work. And now, there are some self-study questions over here. Please go through them so that you can make sure that you understand the concepts that are there. Any of the PowerPoint which do not work, we're going to remove it, and all those are available under watch. Okay, so don't feel upset that it's not working. I will just correct it and upload the PowerPoint presentation. And with that, I'm going to stop the share and end this session.